converting an equation written in rectangular form to one written in polar form. Once again, the idea here is that we know we can convert vectors between component form and magnitude and direction, and we know that component form has values that are very obviously the x and y coordinates of the point in rectangular form, and we know that magnitude and direction are the r and theta coordinates of a point written in polar form. So using the conversions that we have between magnitude and direction and component form of a vector, x is equal to r cosine theta, y is equal to r sine theta, r is equal to the square root of x squared plus y squared, and the tangent of theta is equal to y over x. We should be able to take an equation written in rectangular form and manipulate it, play around with it a little bit to turn it into something that is written using polar coordinates. This process is very admittedly more of an art than a science. It takes a lot of playing around and trying to find something that might work out. But one trick that we can use is to try to think about what kind of equation we have and think about how that will affect the result. So for example, I might have something like y equals x square roots of 3. Y equals x square roots of 3 is the equation of a line passing through the origin. And I know that lines passing through the origin have equations of theta equals some constant. So I'm keeping that in the back of my head and looking at this formula over here, tangent of theta equals y over x. I've got a y, I've got an x. If I can do some creative rearranging, I might get that y over x equals the square root of 3, and then substitute in, replacing that y over x with tangent of theta. Right? If tangent of theta is equal to the square root of 3, then theta itself is the inverse tangent of the square root of 3. And I remember that the inverse tangent of square root of 3 is pi over 3. So y equals x root 3 in rectangular coordinates is the same thing as the polar equation theta equals pi over 3. As another example, we might look at x squared minus 2x plus y squared is equal to 0. Again, there are a couple of ways that you can think about this one. What I see right away in this equation is that we've got x squared and y squared going on. And when I see x squareds and y squareds, I immediately start thinking about that r equals the square root of x squared plus y squared. So let's get that x squared and y squared together. And then that leaves this extra 2x behind. All right, I can deal with an extra 2x if I don't accidentally flip the page. Sorry about that. All right, I can deal with an extra 2x hanging out here because I also have the formula that x is equal to r times the cosine of theta. So those are the two substitutions I'll use. Right? I know that r is equal to the square root of x squared plus y squared. And if I square both sides of that equation, I get that r squared is x squared plus y squared. And that substitution is coming in right here. And I know that x is r times the cosine of theta. That substitution is coming in right there. So I get that r squared minus 2 times r times the cosine of theta is equal to 0. Now we could end the situation right here, but this one actually can be cleaned up a little bit further, because I noticed that there's a common factor of r on the left-hand side and the right-hand side is 0. And whenever I have a common factor and I have a right-hand side equal to 0, I immediately think about using the zero product rule. Which lets me split this up into two possibilities. R is equal to 0, or r is equal to 2 times the cosine of theta. Sometimes it turns out that I need both possibilities and there's not really anything else I can do. But notice in this particular case that when theta is equal to 0, these two equations both give me r is equal to 0. So r is equal to 0 is kind of this awkward point. It's only the point at the very center of the polar graph. It's only the origin. So theta doesn't really matter for r equals 0, which is why I'm very happy to get it out of the way and give my result simply as r equals 2 times the cosine of theta.